now I can start.
It's okay, you can start whenever you want, so you can just trim the first bit off.
I'm gonna improve the friction. Alright. No, this is like are you finished texting?
I'm done now.
Okay. Ladies and gentlemen. Ladies and gentlemen, welcome to the last meeting of the physics club. Chris is not here, so I have to say it. Alright, and yeah, so today I'm going to talk about electronics. And as you probably know, it's meant to be like the introduction to the next talk I'm going to give you the next term about transistors. But today we're going to see a transistor as well. And we're going to see like so much exciting stuff, like also not transistors, also diodes, capacitors and everything. Like it's going to be very exciting. And you've got cookies as well. Well, I want to say something more. I forgot. It's going to be. Oh yeah, I want to say that it might be quite long, but it's a very special talk. It's the last talk of the term, so I hope you're gonna forgive me that. You're gonna enjoy it anyway, so you're not gonna even notice that it's longer than usually. Right. So I start. So why am I giving a talk about electronics? So it's like it's obvious, right? I don't have to say why it's useful, because like use it every day. Like she's got her cell phone ringing, and we can view this talk because of electronics. Because I've got a laptop, we've got this projector, right? And our YouTube viewers can view this presentation because of electronics, because they're looking at the laptop. So without electronics, like the world wouldn't be the same. Right, and transistors are very important in electronics. They were invented in 1947, and in 1956, the people who invented that won a Nobel Prize for that. And they are used everywhere. They are used in amplifiers, for example. So for a guitarist, it's really interesting, and also for other like musicians. And they're also used in logic gates. So each processor in each computer consists of lots of transistors. So you see, they are very important. So that's why it's worth listening about them, and about other electronics as well. Alright, so the first topic, so is everyone, like I'm asking Sarah actually, is everyone okay with Ohm's law in my audience?
With what?
Ohm's law.
Oh.
But don't worry, I'll catch up as well.
You won't catch up, so you, like,
No,
okay,
I'll just keep going, I'll figure it out.
No, I have to explain to her. So for each of you, it's going to be a recap of high school physics.
I might know it, I just can't remember.
What do you study?
Chemistry.
Chemistry.
So the Ohm's law is a relationship between three most basic quantities in electronics. There is voltage. You know what voltage is? Voltage is like potential energy of a charge, but per unit charge.
Mm-hmm.
And you might have voltage like between two places, like from here to here, for example. So voltage, there's potential. Potential is at a point, like there's potential here, there's potential here, and voltage is the difference of potentials. Voltage is always between 2 points. And you might have some element, like whatever, between these points. And if there's a voltage between them, the current flows. Well, okay, yeah, let's say the current flows. Okay, so the voltage the voltage is V between these points, and the current I flows. And the relationship between current and voltage is that the current that flows through this is the voltage divided by the resistance. And the resistance is the property of this object, and it measures how difficult it is for the current to flow through the subject. And we measure voltage, we can measure voltage, we can measure current and resistance using my beautiful multimeter, which you can see here. Can you? Yeah. So, has any of you played with this, like, in your spare time in high school or something? Like, none of you?
Yeah, in physics labs or electric
Yeah,
labs.
for example.
I
So, for example, we can measure some voltage. Like, okay, I'm just checking you, alright? So, if the questions are too easy, then like that's because I'm checking you. Okay, who knows what the voltage is across a normal battery like this?
1.5 volt.
Exactly, and we can measure that. So, it's set up the right way. Sarah, can you help me?
It's punishment for leaving sleep.
You have to hold the battery, and
Okay.
I'm gonna measure the voltage across the battery, and you see it's 1.5 volts. Yay! It's only 1.6. But when I connect something to the battery, it's gonna the voltage is gonna drop slightly because it's got internal resistors. So it's gonna be effectively about 1.5 volts. How about this battery? That's the bigger battery. That's 9-volt battery. And okay, this one can stand on the table. And of course, it's got 9 volts. Bit more. Alright. That's okay, now I need a volunteer. Now we're gonna measure some other voltage. It's gonna be interesting. Because that's boring, like everyone knows that. Sarah, come. Now we're gonna measure the voltage across Sarah. Sarah, could you grab with one hand one electrode and the other? Yeah, but you have to hold the metal. And can you see that? It's in millivolts now. Who's got an idea? Like, where is this voltage from?
Where does the voltage come from?
Yeah.
From the sodium-potassium channel closing and opening.
No. If it was the case, then if we shorted it out, it would still be there, but it wouldn't be. It's definitely across Sarah. It's because Sarah...
The heart.
The heart. Sarah has got a heart. And the heart acts as an electric dipole. Effectively. It contracts, it does some crazy stuff. I don't know about this stuff. Chuck Miller is better than that. But then I know that it acts as an electric dipole. So if you've got Sarah... If you got Sarah here, and if we measure the voltage from one hand between one hand and the other hand, and there's the heart, it's like an electric dipole. So you can draw the dipole field lines. So that's the electric field. And if there's electric field, there's potential, like in around Sarah. So in principle, there's potential difference between one point and the other point of Sarah. And that's where this voltage comes from. And that's the main principle behind EEG, the diagnostic technique in medicine. They attach electrodes to your body, and they measure potential differences. And they can actually detect like which frequency or which signal comes from which part of the organism. Right?
Does that mean if you put our hands close together, like just judging by the dynamic film, then you have a stronger reading? Or
Well, it's not that easy. It's not only the heart, it's also muscles and the
Right.
brain and everything. Everything creates its own electric field.
and shouldn't it vary with time?
Yeah, and it did. Like, see?
But it's okay.
Alright.
Alright, sure. shouldn't it change sign with time? So minus.
Did it change sign?
I thought it
I
was.
think it was. Well, like if I.
Unless you're in AC, I don't know.
You know, maybe there's some other effect, I don't know. If I change hand, yeah. Oh, it's not. Yeah, I think it just changes sign.
Okay.
Maybe it was just coincidence that it didn't. And maybe there's some other effect that I'm not thinking about now. Right. And I forgot to mention that. Okay, so you know Ohm's law, physicists, but do you know voltage current characteristics? You know what that is?
You plot V against that.
Yeah. You plot V against I, so it just tells you what V would you have for different I's, or what I's would you have for different V's. So for a resistor, for example, it's just a straight line. Sorry, you know why it's a straight line?
Because it's got a
So
constant gradient.
V I. You're a chemist, so I don't know how
Yeah.
quick you
It's
are.
got like,
Yeah, because R is constant,
yeah.
and V is IR. So the gradient is the resistance. But we're gonna see in this talk later, we're gonna see some more crazy VI characteristics. Yeah, okay. Oh, yeah, and in electronics, if in case you don't know, I'm always afraid that I'm saying just obvious stuff, but you know, I have to make sure. So, in electronics, people usually don't draw the whole circuit. Like if you have, for example, a voltage divider circuit. So in physics, you would draw it like battery. There's a resistor, the other resistor. Here you have some load, and it's complicated. And in electronics, we don't draw the whole circuit. We just draw this part. That's plus. We draw just connect to ground, that's 0 volt, and here the load is just like the output. So this is the output. Right? I'm just saying of this stuff. Okay, so now it's gonna. I hope it's gonna get more interesting. So let's start with some very basic physics about electronics. So I'm gonna ask you a question, and you tell me the answer. So we draw currents in circuits normally in physics. So which way do the electrons go in the circuit? Is it the same way as the current, or the other way?
The opposite.
The opposite. Like if you have a battery, plus and minus usually draw current going from plus to minus. But electrons are negative, so they go from minus to plus. So keep that in mind, because in diodes it might be a bit confusing. But I try to make it not confusing. Right. Okay. Now, who's not familiar with the band theory of solids? The band theory of solids.
The band theory of solids.
Yes, finally, there's someone like, yeah. Okay, now I can. That's how you are. You're a chemist.
No, a tiny bit.
All right. Okay, so as you know, we've got 3 types of solids. And if we distinguish them with respect to conduction abilities, let's say. So we've got conductors, we've got insulators, and we've got semiconductors. And what's the difference between them? So you know that conductors conduct current, insulators don't conduct current, and semiconductors, like, they conduct, but not that good as conductors. Right, so each solid consists of the crystal lattice. So it's like, okay, let's start from a different thing. Like if you have a molecule and it's got some orbitals, okay, so I'm going to draw an energy diagram. Now a chemist would be better than me at that. But so if you have one molecule here, there's energy diagram of this molecule, of one atom, and that's the other atom, and here are energy levels of this atom. And if they are the same, if they connect as a molecule, you've got hybridized orbital, right? Let's go that way. So these levels are the same at the same level, but they can't be they can't have the same energy because there's Pauli exclusion. Because they can't be the same. If we have one electron here with spin up and one electron here with spin up, but they can be in one molecule. There can be the two electrons in the same state. So actually, what happens is that these two orbitals hybridize, and you've got one here, one level here, and one level here, higher and lower. Let's go sigma plus and sigma minus, right? Or
What?
sigma plus and sigma minus, for example, right?
Yeah? Depends.
If it's S, but never mind. So and for each of these levels, you're gonna have a pair, like, right? Okay, and if we add more atoms, like you have in a solid, you've got lots of atoms next to each other. If you add more of them, you're gonna have a third atom, so you're gonna have a third level here, and so on. And in the solid you've got loads of atoms, so actually these levels add up to something called a band. There's loads and lots of levels here, and as well loads and lots of levels here, and these are the bands. And actually it turns out that there are usually in a solid there are only two bands. So these levels here just overlap with each other, and there are just two bands. And the one below is called the valence band, and the one above is called the conduction band. So it's not that they are like physically one above the other, it's in energy, right? So this one has got higher energy, that's the conduction band, and this one has lower energy, that's the valence band. Oops. Yeah, and okay. And between them there's a region in which there are no states, and this region is called the band gap. So no electrons can be in the band gap. They can either be in the valence band, and they can be at each of the level of the valence band, or they can be in the conduction band, but nowhere in between. So it turns out that the band gap is the highest for insulators. Then for semiconductors it's narrower, and for conductors there's no band gap. This conduction band is just on top of the valence band. Right, and in the valence band there are lots of electrons. They just sit there because it's like a ground state. There are lots of electrons here, and here there are none. But unless they get promoted to the conduction band, for example with a photon, you can send a photon, and this is gonna promote one electron to the conduction band. If the energy of the photon is like higher than the band gap, or it can be. Alright?
Yeah, I'm alright.
And it might be also promoted by temperature, for example. So actually, yeah, in any solid you've got some electrons in the conduction band because they were promoted by temperature. But in insulators you've got not too many electrons because the band gap is so high. So if you have temperature here, and this gives like energy to these electrons, but there are these like energy impulses have to be high enough for it to be possible to promote an electron to a conduction band. Yeah. And for semiconductors, the bandgap is narrower, so there are more impulses that are high enough in energy to promote the electrons to the conduction band. And in conductors, like, you just have a lot of electrons in the conduction band because there's no bandgap. And in the valence band, there are so many electrons that can't conduct, they can't move. Because it's like full of electrons, this conduction band, this valence band. And in the conduction band, there are not too many electrons, so they can move. And so, you know, the more electrons you have in the conduction band, the better conductor you have, because you have more carriers, more free carriers. Okay, is everybody okay with that? Or do you get any questions? I forgot to mention that. Yeah. So if one electron, let's say we have one electron that was promoted to conduction band, and what you have here in the valence band is a hole. That's a hole. So it's like I'm gonna always draw holes in green today. So there's a hole. So a hole is like there was a minus charge there. There's a sea of minus charges. But there's a hole, so there's one missing. So effectively you can view it as a positive charge, but in a sea of zero charge. Or you can view it as zero charge in the sea of minus, of negative charges. But we're going to view it as a positive charge. And this hole actually, it turns out it can move, right? Because it's like, you've got some atoms, and there are electrons around them, and there's one hole. So there's one electron missing. But then this electron can jump here, so effectively this hole has traveled here. So that's how holes move around the conductor.
Just a question before. So you said because of how many electrons are there at each level? Because like the Pauli exclusion principle should be 2, right? So you mean that there are 2 in each?
Yeah, yeah. But there are so many levels. Like you have.
But yeah, so they look very close together.
Yeah, yeah. You have like Avogadro number of atoms, and for each atom you've got so many electrons. I mean, so many states. So there are like zillions of states in one band. So it can be treated as continuity.
Okay.
And like if this level in hydrogen is about, what is it? Is it 10 eV more or less, minus 10 eV? This level. So the width of one band can be like, let's say, 3 eV. The band gap is also about 3 eV. This is also about 3 eV, like more or less. And these states are squeezed in there.
Okay.
So here you have, oh, I forgot to show it. That's the first transistor. Actually, it's a replica of this first transistor that won Nobel Prize. Yeah, and here are band gaps for various materials. So you've got diamond, that's an insulator, and it's got a high band gap. So there's 5.5 eV between the conduction band and the valence band. And because of this, there are not so many free carriers in the band gap. There are not so many free carriers in the conduction band, so that's why it doesn't conduct electricity very well. And if the band gap is about 3 eV or less, it's called a semiconductor. So here you have some examples. There's silicon, there's germanium. These are the most commonly used. And why is that, like, why is 3 eV such a special number? What energy does a photon of light have, of visible light, more or less? Which one is, like, which one has the highest energy, blue or red? Blue. So if a photon energy is hc over lambda. So it's, what is it, 6.6 times 10 to the minus 34 times 3 times 10 to the 8 over, and what's the wavelength of blue? 400 nanometers, so 400.
And divide by 1.6 times 10 to the
Yeah. So you're gonna see that. So 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 400 times 10 to the minus 9. You can see it. So that's in joules. And now I divide by E, and I get 3.1 volt EV. So you see. So the most energetical photons in the visible light are about 3.1 EV. So if you put a semiconductor, like made of silicon for example, it's got a band gap of 1 EV. So by just putting it in the light, you've got promotion of electrons into the conduction band. So you've got many electrons in the conduction band. If you put a diamond just in the light, it's not going to do too much, because the photons are not energetical enough.
But why is blue light so special?
Sorry?
Why is blue light so special?
I just took the most energetical wavelength in the visible light. If I took red, it would be
Why
smaller.
visible?
Because we're living in the world where there's visible light around. There's not too much UV around. There's lot of visible light.
But there is lots of invisible light.
Yeah, but UV, there's not too much UV around. There's more visible light.
If you take a diamond outside in sunlight, will it conduct electricity if there's enough UV around?
Yeah, if it was, it would become maybe sort of semiconductor. It would have some carriers, but maybe not too much, because it's 5.5 eV, the band gap. You know, just ask questions, like it's just physics class. Yeah. What's next?
If you change the temperature,
Mhm.
and would you make diamond using that?
I don't know which way it's gonna go, but I saw actually a video on YouTube that we're gonna get to that later. But it turns out that LED diode emits the light which is of the energy of the band gap, and they put a diode in liquid nitrogen and it changed color.
Oh wow.
So yeah, so by changing temperature you can change the width of the band gap. I don't remember which way, but yeah, if you could lower the band gap, then you could make diamond as a semiconductor.
What is the band gap of conductors?
0. It's when the conduction band is just on top of or even overlaps with the valence band.
Okay.
So in conductors you've got lots of free carriers, because any kind of energetical impulse will just send the electron to the valence, to the conduction band. Okay, so there are only physicists here, so... Oh, that's a good question. So, okay, so now you know that the current consists of electrons, and they are moving in the circuit, no doubt. So, for example, you've got a wire, and there's an electron, so it's moving. But so there must be a force acting on this electron. Yeah, okay, it can move with the... If it was moving without any force, it would collide with the crystal lattice, with other electrons, and it would stop eventually. But it doesn't stop, it's moving. So there must be a force acting on this electron. So there must be electric field acting on this electron, right?
Well, it has to be filled with the exponential difference.
But the Gauss's law tells you that there can't be an electric field inside of a conductor. So how can you have a field here? Because the Gauss's law tells you that You know the gases law? Yeah, so yeah. So it's that way because always when there's E fields in the metal, because there are some E fields in the metal and you change it, and then the free electrons just rearrange themselves so that the E field is zero. The net E field is zero. But here it's not zero, definitely.
Well, I know that electrons move at the edges of the metal, but
Say it again.
the electrons move at the edges of the metal.
They move throughout the whole metal. It depends on the current. So in high frequency AC current, they move throughout the edges. But in DC, they move throughout the whole metal. Alright, so the gaseous law works just in thermal equilibrium. No, not in thermal, in equilibrium. So it's when electrons doesn't move. So it works for static charges. When you have some metal, for example, you apply some external electric field. So at the first moment, there is some electric field through the metal. But so this is not equilibrium because there are forces acting on the charges inside the metal, and then they rearrange themselves so that the E field is zero inside. And from that moment on, there's equilibrium. But before they rearrange themselves, as long as they're moving, there's no equilibrium, so you can have E fields.
So there's two different fields, right? There's a field externally applied, and there's a field because of the electrons moving.
Yeah, because there's
So really-
Coulomb force and yeah. So there's field of these charges. And here they are still moving, so it's not equilibrium. It's a steady state because the current flows that they have that's like steady flow. They're flowing with constant velocity and so on, but it's not equilibrium. Okay, now the next question. You've got a circuit. So okay, so what is this E field due to? It's due to the battery, right? If you so now we've got the battery here, plus and minus, and for example you've got a wire like this. So it's gonna be you can view the battery like electric dipole, right? You've got plus, you've got minus. So the E field of the battery, it looks like this. So what is going to be the direction of the E field in here? To the left, right? How about here? Also to the left. And here, to the left. Just smaller and smaller and smaller, but to the left all the time. How about? Yeah?
Sorry. I'm just looking at the way, if you draw the other side of that,
Yeah.
so if you copy that. Surely you mean the copy is the E field the other way around.
It must be.
Yeah.
That's like, sorry for the mess on the board. So definitely it's like
It's to the, well, according to that diagram,
Mhm.
it's to the right? But then according to,
if you had some electron here, it would clearly move to the plus of the battery, so that's okay. But here it would clearly move this way. Here it moved this way. So there would have been a charge buildup here. But it doesn't happen. Normally the current flows just around the wire. So how can it flow around? How can it flow through this bending point?
Because the electrons make the electric field. The electrons which are
Yeah. So actually, it turns out that there's a static charge in the circuit at the surface of the conductor. When you attach the battery, this static charge establishes just around the circuit, and I'm going to tell you how it is. It's negative next to the negative side of the battery. So it's got high density here, and then lower, and then here it's 0, and then there's a static charge on the surface here. It's positive, and it's plus. So this charge is at the surface of the conductor. And it's really there. I've seen a video, there was an experiment. They did it with high voltage, and they could measure this static charge. I mean, they could experience it with like aluminum foil. And this static charge, it's like this. This is the wire, and you've got these rings of charge at the surface of the conductor, and next to the negative side of the battery, here, this is high density of these negative charges, and then lower density, and then in the middle it's 0, then it's positive, higher density, and there's the plus side of the battery. So you'll see that inside these rings, the effect is always in this direction. Because, well, the force acting on the electron is in this direction, because it's always attracted to the more positive charge. And it's really like that. So in our circuit, it's going to look a bit like that, the static charge on the surface. And notice that around each bending point there's also higher density of charges, because the electron has to make this turning, right? So it goes through this, and then it's repelled from these charges, so it can turn, and then it's attracted to places with lower density. Then it's repelled from these charges because it's high density, and then it goes, and then it's attracted. Oh, it should be probably here. Yeah, okay, so then it goes. And it actually makes sense. So, okay, sorry, I made a mistake. So these charges should be here, on the other side, the positive ones. And these here, and these here, and these here. And it makes sense from electrostatics, right? Because there's always a bigger charge density around the edges, around surfaces with lower radius of curvature. So the density will be smaller here, but higher at the edge. And these charges just come from, these are just the free carriers in the conductor. Some of them always end up on the surface in order to make it possible for the current to flow. Right? So that's why they say every circuit has got its own capacitance, because there's always some charge buildup. Also, they say that every circuit has got its own inductance, as long as it's AC circuit. So if you have some circuits, you always have some loops. You got some, I don't know, plus, minus, you've got some resistor, another resistor, ground, whatever, a light bulb, for example. Okay, and it's connected to a ground here. And you put AC through this. So it doesn't have any inductor. There's no inductor in the circuit, but it still has some inductance, because the AC current is flowing around this loop, so it produces a magnetic field. But if it produces a magnetic field, there's a changing magnetic field flux through this loop, so there is back EMF, and that's where the inductance comes into play. So there's always some inductance in each AC circuit as well. Yeah, okay. You want another trick question?
Yeah.
Okay. So you're gonna have two batteries disconnected, totally disconnected. Oh, it takes so long to... Okay, I can start telling you. So you've got two batteries, totally disconnected from each other. So you take one of them, you take my voltmeter, measure the voltage between plus and minus, and you get 9 volts, right? You take another battery, you measure the voltage between plus and minus of this battery, and it's 9 volts. So how about this? If I took this one battery, that's plus and minus, there's another battery, plus and minus. What if I took the voltmeter and measured voltage from here to here? Will it be 9 volts?
Let's
Will it be 0?
It's hard to say. You
Yeah.
can say.
So what do you think? Shall we vote? Who's for 0? So the question is not is there a voltage, but what is it going to measure? Because that's going to turn out to be important. So what is it going to read? Just
So, you said it was like two capacitors in the thing, right? So is it going to act like... I think it will be like 0, wouldn't it? Or if it was like two capacitors.
maybe.
Wait, why are there capacitors?
Because of the diagram that he's...
Well, dipole, yeah. Like there was dipole here and dipole here.
Okay.
But look, if it was 0, clearly there's 9 volts between here and here. So what will be here? If it's 0 from here to here, it must be minus 9 or plus 9 volts between here and here.
Well, doesn't just depend on the battery.
Sorry?
That doesn't just depend on the batteries you're using.
The voltage, yeah, but I mean, is it gonna be?
I don't think you can answer this question without defining which point is grounded. You have to say that on the left battery, one of the diodes has to be defined to be grounded. Then do the same to the right battery, and then...
Hold on, I didn't finish. So,
Well,
yeah, this depends on the battery, but I'm saying that if it was 1.5 volts, then still, if it's 0 measured by this voltmeter, it
it's
should
not
be.
what I mean. I mean that you have defined as, I don't remember your name, but
That's
you were
right.
saying there is defined the potential difference, but the potential each point is undefined. So you can't.
Yeah, but I measure the voltage. So I literally take one battery, another battery, and measure voltage between here and here. So it must read something. Is it going to be 0? Or maybe plus 9 volts? Is it recording?